good for everyone. So now, to go over sort of the second part of the overview for this course. So a lot of things about computing have changed recently, and so Moore's law, for those of you familiar with it, basically says that kind of the number of transistors doubles every 18 months. And so computers are constantly getting more powerful and faster, and that if you have any problem today, that will simply be solved by better technology tomorrow. And that's true to some extent, but there are some issues with it. And as you see with this graph here, unfortunately that's not very big. When we look, from 1975, the number of transistors seems to be growing quite well. I mean, you have on a log scale here a fairly linear line, but the clock speed seems to have leveled off. And so there was pretty impressive growth of the clock speed back there, but now computers aren't really getting that much faster anymore. And so what's changing is that there's a lot more processing power that you have, but the ability to do a single task hasn't been improved. And so what this requires is that you are able to divide your tasks up into many little pieces. And so any of you who have a reasonably modern smartphone know that they advertise these phones with having 2, 4, 6, 8 cores, which means that your phone can do 8 different things at the same time, because that's more efficient use of power and it's easier to make chips for. And if you're able to parallelize what you're doing, you can get massive benefits from it. So having a single chip that's very, very fast uses a ton of battery power, while having a bunch of smaller cores that are slower lets you accomplish the same, if it's a parallelizable task, in a much more efficient way. And so really what's happened is that you have multiple cores. Many times you have multiple CPUs. And then the final modality, which is very critical for those of you who are interested in deep learning, is this sort of new modalities. And so you have chips like GPUs or sort of custom chips that go beyond this, which are designed to be incredibly parallel. And so if you look at what a GPU or typical graphic processing units do, they are much slower and much stupider than CPUs. So their speed is very limited, and the operations that they can do is also very limited. But they benefit from the fact that you can have, I think, 4,000, 6,000, 8,000 cores on a chip, which means if you have tasks which can be divided, you can do them much, much faster because you're able to benefit from the fact that you have 8,000 things doing it. And so if you're trying to do one thing, a GPU is completely useless because it doesn't support a lot of different operations and it makes it very difficult to do it in a massively parallel way. But if you're doing a lot of little tasks that are very similar, and this comes in matrix multiplication, in calculating convolutions, in a lot of these kind of operations, and that's where GPUs then really, really excel, because you're able to divide them into a bunch of small little tasks well. So computing has changed as well. So cloud computing, as you see from Binder, is becoming more and more prevalent and popular and is much easier to get started with. And so here, with one click on a link, you now have a computer that's set up with exactly the right version of Python, all of the packages you need, all of the data sets that might be relevant, and you don't have to do any of this configuration yourself. And we know that everyone has exactly the same setup. And so it makes life much, much easier. You then have the other issue of, if you buy a big expensive computer, it's probably going to be underused most of the time. And so, particularly from my experience at, Paul Scherrer Institute or the Institute for Biomechanics, when the week before abstracts are due, the cluster has a wait list of, months to try to get anything done. And then the day after abstracts are due, it's completely empty because no one's interested in running any results anymore because they've already submitted their abstracts. And so obviously that's not a very good use of computing resources because you don't have enough when you really need it. And then you have too much most of the time because most people in your lab, at least in Switzerland, don't work on weekends and don't come in on Saturday morning to make sure their job ran correctly. And so with these kind of services, you're able to benefit from sort of much more of a sharing economy of you get resources when you need it and you give it back when you don't need them anymore. There's a number of different providers here. Obviously, the biggest is sort of Amazon, Google, Microsoft. But even in Switzerland, there's companies like Switch, which offer cloud solutions. And basically, the main focus of cloud isn't about being Amazon or Google. The focus is much more on you don't deal with infrastructure problems. And so if you look at all the computers in this room, someone has to go through and make sure that their drivers get updated. Someone has to make sure that the video card still works, that the hard drive gets replaced when it's corrupted. And with cloud, you outsource all of those tasks in the trade-off that you pay a little bit more for the services. And so if you use a computer full-time all the time, it's potentially cheaper to do it yourself. But when you include the cost of going through and manually changing these hard drives and updating these systems, it becomes quite expensive quite quickly. The main reason it works so well at ETH is that PhD students are very poorly paid, and master students aren't paid at all. And so you have lots of very cheap labor to do this for you. But if you had to pay professional IT to do a lot of these tasks, it would be incredibly expensive. And so, depending on what performance criteria you're looking at, it has different bottlenecks. And so a lot of the main issues you have with this is data size and data privacy. And so size is one of the bigger issues where if you're dealing with 8 gigabytes a second and you have a 1 gigabyte a second connection to Amazon, then every second you're 7 gigabytes behind. And so you have a huge issue getting the data up quickly. The second major issue you have here is privacy, where when you're dealing with medical data or personal data from people, it's very strictly limited what you're allowed to do with them and where you're allowed to send them. And so for hospitals in particular, there are some rules you have where patient data can't leave the canton, which if you're somewhere like Basel-Stadt, and that means you can't send your data to Basel-Land. And so you have a very tiny little region where you're actually allowed to send the data and everywhere else you're not permitted to. And so it makes doing things like cloud computing, of course, very difficult because legally you're not allowed to send the data there. I think I'll skip the cost part, but basically you can do the formula, or you can do the math based on what tasks you're doing and how expensive the resources are, and see very quickly how much you pay to have a machine in the cloud and how much you have to use a machine that you buy locally for it to be worth it. So here we have sort of the course overview. It's not very. The lectures will probably change a little bit, but the general overview is the sort of the introduction and workflows is today. Image enhancement is next week. The week after will either be basic segmentation or sort of a deeper introduction into some of these Python tools, depending on how the planning works. And then advanced segmentation, and so how do you go beyond sort of the basic techniques. Single objects, complex objects, many objects and distributions, statistics, prediction, reproducibility, dynamic experiments, and then scaling up in big data. And so the idea for scaling up in big data will really be focused on a lot of the things we've covered before, but that lecture will specifically focus on how we change the tasks that we've done to handle that. But if you do everything right from the beginning, it makes it a lot easier to make that transition than if you sort of start off with something else and then at the end decide, oh, it might be important to scale that up. And then come sort of the guest lectures and the final presentations for the class. So those are the specific lectures. If you have questions, you can ask, and then sort of the wrapping up. So now to sort of go into more concretely, what is an image? So I guess at least one of you admitted to not having any familiarity with image analysis before. And so we'll start off with an incredibly abstract, fairly useless definition, where we say it's sort of a pairing between spatial information and some other kind of information. So we call the spatial information here the position, and the other kind of information the value. And so in most cases, this refers to 2D position, so kind of XY coordinates on a screen in this case, and a numeric value as sort of intensity. And so here, if we look at a basic image, we have, wow, these things show up so small, a number of, a table full of points, and we have an X position, a Y position, and an intensity at each one of them. We can then render that as a image or as a matrix view, which is sort of what we're much more familiar with looking at, that if you go to a table, this is very difficult to visualize what this might be. And if you go to this looks much more familiar, where you now have all of those pixels sort of presented in an array format and a sort of color map associated with it. And so the next step here is to sort of apply the color map. And so the lookup table is what it's also referred to as. And so this makes it much more interesting. So if you just have an array with numbers in it, that's not very useful. And having a lookup table makes it much more useful. And so we have this example again here, where we have all these different numbers in the table. And we use this mapping called, I think, Viridius, which is uniform perceived scale, I think, of plotting the different intensity values between 0 and 100 as a color between blue and yellow. And so with intensity images, these colors are sort of arbitrarily assigned. So there are no intrinsic values for this image that say that has to be that color, and you can change to any color map that might make sense. And so here, if you change this to hot, you then get a different plot there. You can change it to, there's a whole jet, which is sort of the MATLAB default color scheme. You can change it to blues. And so depending on the kind of data, you can make completely different representations of what you're looking at. And so yeah, it's based on what you're trying to visualize, who might be looking at it. And so of course, this again will be something we cover again in the later lecture. But if you're dealing with someone, or if you're dealing with people that potentially have color blindness, certain color schemes are very poorly suited for people who are colorblind. It's very difficult for them to tell the different shades apart. And so it makes it a lot more difficult for them to look at what you're showing them. And for many cases, sort of a linear color scale doesn't necessarily make sense. And so yeah, so here we show some example other color scales with hot, jet. And so the idea of a lookup table is formally that you sort of have an intensity and you want to map this intensity to a color. And so here we show 3 different lookup tables. You can look at the code if you're interested, but the focus here is much more on we have an intensity between 0 and 1 for our signal. And now we can show on sort of the y-axis what that red component is. And so there's no requirement that this is linear. There's all sorts of different functions that can be used based on how you want the person who's looking at your image to perceive it. And so, with this blue scale, this is not linear at all. It also sort of saturates there. But for a human eye, it's perceived as fairly linear because of the way sort of the cone cells in your retina actually function, or rods and cones in your retina function. And so it's important to be aware of these different mappings and that some of these different mappings might change what you see in the data. So this is really the important part, because here, you don't have very much sensitivity, while here you have a lot of sensitivity. So small changes in your intensity will appear bigger at different points on this scale. And that's particularly true of sort of these default schemes like JET. Where was that? Anyways, I thought it was there. Which wasn't necessarily designed to be used as sort of a consistent interpreted scale, where you have small changes that, the difference between here and here is much bigger than the difference between there and there. Which means when you're trying to interpret your image, or you're trying to understand what features could be important, your eyes will sort of trick you. And so just sort of aware of this. These can be nonlinear. Oftentimes you use kind of a log relationship. So, just like with the sound scale where you have decibels, you can use log transforms in images where you really want to focus on sort of covering a number of different orders of magnitude. And so if you use a standard scale to cover a signal like, this intensity, you'll have all of your changes in colors happen, and then sort of the saturation, whereas if you use sort of a log transform, you're able to make those spread out better over the signal. So for an actual real image of bone, you can take sort of the same image and give it a number of different color scales, and different things get perceived differently. Here you see a bone that has lots of holes in it, whereas this one, those holes are much less present, and this one, they're almost invisible. And so if someone were to look at this bone, they might say that this one looked like it was very weak, this one was medium, this one was strong, when in fact they were all exactly the same bone. They just had a different color scale that was applied to it. And so that's where you need to be important when you're looking at picking these color scales, that they do an accurate job of representing the data that's underneath them, because it's very easy to pick these and have it change how someone would perceive the data fairly significantly. So for 3D images, we just had 2D images there. It's the same sort of idea. So you just add an additional dimension to it. And so here you have sort of a very small 3D image of 3 by 3 by 3 by 3. And we show it as sort of a matrix representation there. You can be rearranged to make sort of one big 2D image, which is often how we look at it. It's something called a montage, where you now sort of flatten out that 3D image so you have all of it there, and you can present it on one slice. And that's also what we showed earlier when we had the different slices of the images. Multiple values is then really kind of the last type of image we'll cover, where instead of having a single intensity at each point, you'll have multiple intensities at each point. So this already applies to sort of images from your phone or camera, where you have a red, a green, and a blue value at every point. And so it's not just an intensity, you actually already have a color that you're dealing with. Many images on a computer also have a fourth channel, transparency, so that when you have an animated GIF that you can put on top of an Instagram message you're sending, and it doesn't take up the full box, that's because it has a transparency channel that allows you to sort of overlay it without having it block everything out. For clarity, we call this sort of dimensionality of the image, or we call the dimensionality image the number of spatial dimensions, and the depth the number and the value. And so when you say, you have a 3D image, it does, a red, green, and blue 2D image is not a 3D image. 3D refers to the fact that you have 3 spatial dimensions, and the depth refers to the fact that you have multiple values or multiple colors. So here, a very simple example where you sort of have an intensity and maybe some other value called transparency. You have it as a table presented there. And then you can render it as images where, you can show the intensity as one image, there's transparency as another image, or you can show them sort of overlaid where you have the transparency set as the size and the intensity set as the color. This taken to an extreme is called hyperspectral imaging. Has anyone heard of this before? No? Okay. So this is then where you have an entire spectrum at each point in your data set. And so each point has a position, so a spatial position, and an entire spectrum associated with it. And so here's an example from sort of an experiment where we were doing Raman spectroscopy of a large sample. And you basically take a spectra at each one of these blue points. We can now load in all of this data where we see we have an X position, a Y position, a wave number, and a value for 210,000 points, I think, in this example. And then we can actually plot it. Here we don't group it by every pixel, but we group it by sort of region. And we see that, at each point we have a whole spectrum of different curves. And so what this gives us about this sample is chemical information. And so if we go back here, we can see sort of what the chemical makeup is of every single point by taking this spectra and doing something with it. And so it gives us sort of the full amount of information that we need to process in order to do some kind of analysis with it. Yeah?
How is this picture taken? I mean, it's just from the, the information, the wave, where does the wave number come from, basically?
Oh, so the information is not collected in a particularly fancy way. So basically the instrument that collects this, you have a microscope and you have piezo motors that control the stage. And so you take a picture like this, you take a spectrum using a spectrometer at a point, which is how normal spectra are taken, and you then move the stage slightly and take another spectra, and then move the stage slightly and take another spectra. And so for each one of these points, you need to take one of those spectra measurements. And because Raman spectroscopy is not a particularly strong effect, I think it took 60 seconds per point here. And so if you were to try to do this for a whole 3D volume, it could take you days to do the entire measurement. But you can get then full chemical information for your whole sample. But yeah, it's not a particularly fancy technique where you have one snapshot and you end up with all this information. There are some techniques that get closer to that. So if you look at satellite images, a lot of them won't just take red, green, and blue. They'll take a number of infrared channels as well so that you can look at things like water absorption, which is much easier to see in infrared than it is to see in red, green, and blue colors. But yeah, so you get this, and basically what this will tell you is kind of what the chemical makeup inside of each region is. And so here you see, these ones have much more interesting peak structures, which would be worth investigating, whereas these ones are kind of just noise and you could ignore them. And so it allows you to go back and analyze that in a much more clear way. And the important part of that is really that you have an appreciation for where these data come from, and that all of these are images that can be handled in a similar fashion. And so that, hyperspectral is not a completely different type of data that you need completely different tools for. It's just another type of image that you can use the same kind of imaging tools as you used before on. So this will be sort of a brief review of kind of the physics part of this in a very, very simplified engineering manner, where, what is an image and how is it created? And so what we do is we kind of divide images into these different steps. And so the first one is sort of impulse or excitation. So what are you using to probe the material? The second is sort of what is the characteristic of interest that you're looking at in your sample? What is the response that the sample gives for this excitation or probe? And then what system do you use to detect it? And so, all of these can cover a number of different areas. Detection system can be your eye if you're a pathologist looking at a microscope from a tissue sample. But more often than not, it's some sort of, CCD or scintillator or transducer. And so now, if we look, again, these tables are too small, at the standard techniques we have in imaging. If you look at light microscopy, this is the impulse is white light. The characteristic is electronic interactions of the light with the sample. The response is absorption. And so if there is an interaction, the light will get absorbed. If not, it won't. And the detection is then sort of a film or a camera. And, that makes a reasonable amount of sense for X-ray radiography. It gets a little bit more complicated where you now have X-ray light, so much higher energy light as your impulse. You have sort of the photo effect and Compton scattering as the interaction you're probing. So you're not probing the same electronic interactions, you're probing different ones, which is why, bone you can see through on an X-ray, or you can see bone well, and you can't see bone well when you take a picture of your arm, hopefully. The response is kind of this absorption and scattering, which makes the light not make it to the detector usually. And then the detector sort of isn't a camera normally. It's normally a scintillator, which converts the X-rays into something the camera can see, and then a microscope and a camera. You also have, for MRI, it's a bit more complicated because your impulse is now sort of radio frequency electromagnetic waves. Your characteristic are sort of these hydrogen spins that you're looking at. The response is sort of absorption and remission. And your detection is then you have RF coils to detect it. And so, you have all of these magnetic fields, which are used to sort of align the hydrogen in the first place, but actually that's not what you're measuring at all. And then sort of the most extreme on the scale is kind of atomic force microscopy, where, your impulse is a sharp point. Your characteristic is sort of the interaction of this sharp point with the surface, so how the surface interaction looks. The response is sort of either contact or repulsion, so how much is this point being pushed around? And the detection is then deflection of a tiny mirror, which is ultimately measured by looking at how a laser spot moves on a detector. And so all of these are images, but they're investigating different things and they're collected in slightly different ways. One of the things that's quite important, so I don't think anyone mentioned it so far. Is anyone doing scattering experiments at all? Oh, one person, okay. Diffraction, okay, yeah. Well, it fits in this realm. So most of the imaging types we refer to are traditional or direct imaging, where visible images are produced and can easily be seen. So for here, you sort of have your original object there, some sort of measurement that might flip your sample up, invert it, blur it out a little bit, and then some attempt to reconstruct what the original image must have been based on what happened. And again, the code is there just to show you how that was made. This isn't something you're supposed to understand at all, or it's also not perfectly correct. There are some assumptions made there that don't necessarily always hold, but that at least shows you sort of what approach you would take for an image data set like this. So sort of indirect. Is there a slide missing there? I thought there was one. Anyways. Indirect is then where you don't actually record the information you're interested in. You record some sort of information which requires a computational transformation to be made into something useful. So sort of diffraction or scattering is the standard example of this, where you have something that's kind of the Fourier transform of your sample. And so you'll measure a pattern like that, and you'll reconstruct it into an image like this. But even, computed tomography, you measure an image, but it's actually not the computed tomography that you're measuring directly, you're measuring a shadow that you then reconstruct, or radiograph that you can then reconstruct into a 3D volume. And so it's closer, of course, than this, but it's the similar sort of principle that you don't measure exactly what you're looking at. You have to do some kind of reconstruction to get there. So yeah, this was the slide I was looking for, the kind of traditional imaging. You know, you have a lens, you have an image plane, you might have some zoom factor or some blurring or some other things that happen. That's the pathway for it. And the traditional imaging model, you know, you have a light source, a beam profile, sample absorption, microscope optics detector, all of these different steps. So that when you want to go from the beginning to the end, you end up with this big, ugly formula for trying to figure out sort of what your measurement was, or what your output is given your measurement sample. And so all of these different things kind of destroy or change your image on the way. And so those are the things that you need to kind of undo. And so that will be some of the discussion for the class next week on image enhancement, is what you can actually do about these changes that get made to your image. You know, how do you do the opposite of a convolution? How do you do the opposite? You know, subtract a signal where you don't know exactly how high it is not a particularly simple task. So other examples of kind of indirect imaging or computational imaging, you know, tomography, light field photography. And so there's cameras that have multiple little lenses, which allow you to sort of collect spatial information at the same time. So here's an example. I think there might be. So this is one image or one acquisition where you're able to collect different spatial information at the same time. So you can get different focuses by computationally changing the image data that you collect using these micro lens patterns. Or with the new iPhone, you have the same sort of idea where you have two cameras and you're able to take the picture from both of the cameras in order to compute a 3D map of what the face would look like or what the person would look like, and do things like background blurring as a computational rather than as a photographic effect. Diffraction patterns fall in this category. Hyperspectral imaging falls in this category, so that when you do a hyperspectral image, you don't have any raw, you know, image data that you can just look at on your computer. You have to do some sort of processing to get a meaningful picture out. And then, you know, surface topography with cantilevers, so this atomic force microscopy comes again. And so now, what are we actually trying to do with this? And so image analysis is really sort of the core of this course. And there's these sort of three primary approaches that we have. So, you know, an image is basically a bucket of pixels, you know, a big table full of information. And how do you turn it into something useful? And what approaches do you take? And so what we sort of realize is that the approach that you take is largely determined by what your background is. And so if you're a physicist and experimentalist, you'll take a very experimentalist approach. You know, you'll try to model the system as well as possible in order to undo the effects that you've done. If you're a computer vision scientist, you'll take a very computer vision driven approach. And if you just took the Coursera course on deep learning, then you'll probably take the deep learning approach. And so we'll try to sort of appreciate what the different strengths of these approaches are and how to know when to apply which one. And so the experimentalist approach is very much problem-driven, top-down. So kind of how does your model work? What is the model you have in reality? What are the approximations? You know, what is this free space propagation function that you want to use to simulate, you know, how much blurring happened in your image? And, you know, what are you actually ultimately trying to extract? And so, you know, if you're trying to do cell counting, you know, maybe the first thing you'll do is unblur the image or correct for the blurring in the image. You'll get rid of some of the noise, and then you'll look for sort of holes in the structure. The computer vision approach is then much more method driven. And so, you know, how can you come up with features of your image that extract what you're interested in looking for? And this is about kind of having an image model rather than a reality model. And there you try to engineer features for solving specific problems rather than focusing on sort of the whole experimental setup. And so this is where you're doing something like face detection. And so when you're doing face detection, you're actually not very concerned with the optics of an iPhone or the noise levels of a sensor. You're much more interested in sort of what is a face, how can we, find edges and boundaries in a face to identify that well. And the final approach is this kind of deep learning approach where it's incredibly results driven. And so rather than focusing on the method or the experiments or the features, you focus on what are you actually trying to extract from the image. And so how can you optimize whatever it is you're doing to get the best results, independent of what sort of weird things might happen in between. This is biology inspired. So the inspired is in quotes because it probably is nothing like how human brains or animal brains actually work. It was just sort of math that was very loosely modeled after things biologists and neurologists have found. And the idea is to build up both kind of the image processing and the analysis from scratch. And so rather than coming with all of these assumptions about what kind of features you're going to be using, you learn the important features as part of your task. And so this is, of course, essential if you're doing something that's kind of an unsolvable problem from a pure implementation standpoint. And so if you look at something like captioning images, if you have an image, there's the examples from Google where, I think if you look at this, the first articles you find, show and tell from Google, where they have images and they're able to put it into an algorithm, a person on a beach flying a kite. And so this was automatically done by a computer. And, even if you know a lot about image processing, it's impossible to say, at least for me, maybe there's people who know much more than I do, how on earth you would come up with an algorithm that was able to spit out a sentence like that. There's blue, there's maybe some yellow. I guess that could be a beach, that when you see blue and yellow together, maybe that sometimes happens. But to identify that as a kite, how many examples of kites would you have need to see before, or what would you even come up with? It's kind of triangular in shape. It's against a sort of whitish background, which could be a cloud. And then how do you sort of a person, and how do you know that they're flying it? I mean, there's sort of an unlimited number of things you would have to do. And that would then cover exactly one sentence, where this is able to handle, two brown bears sitting on top of rocks, a blue and yellow train traveling down train tracks, and sort of an absurdly large number of different situations that you'd have to be able to handle. Even here, a man riding on a wave on top of a surfboard, where, waves, you'd have to handle different illuminations, you'd have to handle sort of an unbelievably large number of problems that you couldn't take the experimentalist or even the computer vision approach because there's way too many things you'd have to do. And even if you were able to go through and detect things in the image, like a man, like a surfboard, to come up with a sentence from that is then a whole nother problem, that you need to somehow combine all those things together in a reasonable way to spit out something useful. And then sort of identifying unusual events. And so, if you're building a system for a CC camera system at, a train station, and you want to identify unusual events, there's not really a list of rules you can pick. Unusual events are by definition things that don't fit into a standard list of rules. And so how can you come up with a way of expressing what goes on in a reasonable way to find out when something really happens outside of this pattern? So we'll go to the on science part quickly, so where we cover sort of what is the purpose of this and the reproducibility. I think we're still okay on time. And what we're trying to do with this course and why the approach is so important. And so sort of what's the purpose of science? And it's to discover and validate new knowledge. And so Potentially, that isn't emphasized very much in what people actually do during their studies, but that's the point. So you're supposed to discover and validate new knowledge, and you're supposed to do this with the scientific method, because that's the only way we've really come up with so far for showing and convincing other people that the work you've done is meaningful. So if you have a hypothesis and you collect data and then you're able to test the hypothesis afterwards, that's a reasonable way of convincing other people, and that's sort of what all of science is based on. And so, the second part is, how do you build on the results of others so you don't have to start over from the beginning every single time you start a project? And so what's really important for this is, while qualitative assessment is very important, it's very difficult to reproduce reliably and produce at scale. And so if you want to be able to do large numbers of samples, if you want groups in China to get the same results as you get here, you need to have approaches that aren't based on the observer's bias or how an observer decided to do a certain implementation. You want them to be kind of independent of all of that. And so that's where this quantitative analysis is really the best tool we have for performing these kinds of steps. And this is also why fields like psychology have a lot of trouble with reproducibility, because it's very difficult to quantify, what mood a person is in. You can ask them between 1 and 10 how they feel, but that's not, just because you can make a number doesn't mean it's a very reliable assessment. And fundamentally, you're trying to quantify something that's very difficult. Whereas if you, go back to the bubble image, there's a very clear definition of what a bubble is, and it's very easy for someone else to count that and get the same number. So for the science and imaging, so images are really great for qualitative analysis, and our brains are very good at looking at images and figuring out what's going on, but it's a lot more difficult for quantitative analysis. And so, if you measure a temperature, quantitative analysis is easy. The temperature is 50 degrees Kelvin. You can look at the spec sheet for the thermometer and figure out that, the performance of the temperature of the thermometer around 50 Kelvin is plus or minus 2 degrees. So you now have your measurement and you have your error bars in one single step. If you do an image, it's much more difficult to assess, because you might be able to find out something about the noise profile of your imaging system, but to figure out how this affects your final result is incredibly difficult, because there's not a very clear linear process between, what you did at the beginning and your final analysis. And each one of your steps might be introducing more error or more bias into the system, and so it becomes a lot harder. Furthermore, when you're looking at something, if you do 5 temperature measurements, you can average them together. If you do, 5 different pictures of a person coming to the hospital, you can't average them. You end up with, a blurry mess because the pictures aren't exactly the same. And so how can you compare these things in an easy fashion? Because this isn't the same simple quantitative numbers that you normally get. Furthermore, with image analysis, there's sort of problem of too many tools being available. And so if you look, there are thousands of algorithms available. Every year, if you look at, IEEE or SPIE or NIPS or any of these major conferences, there's hundreds of new algorithms that come out every week that are supposedly state-of-the-art at solving some certain problem. How do you pick which of these algorithms to use? How do you evaluate if it makes sense? And how do you sort of combine a number of these different approaches together in order to get reliable results at the end? And so that's where all of this is very important, and doing this well is sort of a critical step. So the last thing on kind of why quantitative, in case that wasn't fully clear for you, which square seems brighter? Any guesses without looking at the code? It's the same. But that's not what it looks like. That's the point. So it's supposed to look, of course, like the one on the left is brighter than the one on the right. And of course, for this, it's funny that they, are a little bit different. But if this was a tumor in your lung, this would be quite concerning that the person who's looking at it can't tell which one of those is brighter if that's what they're using to make a decision on. And so for, scientists, it's quite alarming that you have a very simple picture, and yet our eyes are not able to perceive those two colors as being the same because our eyes are doing some sort of filtering in the background and post-processing that we don't know about that's very difficult for us to quantify. And then sort of are the intensities constant in this image across the different bands? And this one's a little bit harder to see, but basically if you look at these, it looks like it gets brighter towards this edge and darker towards this edge. And that's again some of the filtering that your eyes and brain are doing when you look at this image. And we know it's constantly linearly increasing between -1 and 1. There's no doubt about that. We've programmed it exactly that way. Maybe the projector is doing a few funny things, but we're pretty sure on that production. But still our eyes look at that and see small changes and small shifts that aren't real. And so that's where sort of it becomes problematic to be overly confident in what you're looking at because of those sort of problems. Where'd the last one go? I think there was one more. Oh, okay. I guess I don't have it. There was a very nice one with spots that disappeared. But maybe I'll find it later. Anyways. And so, science demands repeatability, and what we really want is sort of reproducibility. And so experimental conditions can change. Animals and human studies are obviously prohibitively time-consuming and expensive to reproduce. Plus, with human studies, you can't easily share data. You can't give someone all of your patient scans unless your ethical or your IRB approval allows you to do that. If you're dealing with sort of synchrotron data, it's not particularly easy to share 100 terabyte data sets between groups. There aren't IT solutions that make that very easy today. And sort of the idea is that, science is already difficult enough. Image processing makes science even more complicated. And many of these tools, approaches that you need to take are multi-step long and complicated. And so very few scientific analyses are, we applied this one operation and one tool, and we got all the results we needed to publish our papers. Most of the time, it's a number of different results. And if you look at some papers, they did some things in Python, they exported the data, and then did some things in R, exported it again, did a few things in Excel, and then did their final analysis in SPSS, and then made an ROC curve in KNIME. And so you end up with something where, you'd like to believe that they did everything correctly and that at no point in time did anyone use the wrong file or forget to save something or change something without telling someone else. But when they have an analysis like this, it's incredibly difficult from the outside to really be confident that they've done that all correctly and that nowhere along the way, by accident or by sort of bad intention, did something get changed. And it's very easy to see if you're a PhD student at ETH and you have to publish 3 papers before you're allowed to graduate. I guess in some groups it might be more or less. And you have 5 data points that make your results look really bad. There's probably people who would like to delete those 5 data points and then they can simply publish it. And of course, those are the things that you want to avoid because, you might publish it quicker, but no one else will be able to reproduce it. And so it's how can we keep track of everything for ourselves and others, and for at least the people who aren't trying to intentionally game the system or cheat, make it easy enough to repeat the results that are going on. And so if we have this idea of sort of a soup or a recipe, if you have a simple soup with these 7 instructions, how can you go about making that soup? We'll skip the complicated soup for now. And that's where we can use this idea of flowcharts and workflows. And so here you have your soup. You buy vegetables, you buy meat, you chop vegetables, you heat water, you add vegetables. And so you're able to express everything that you're trying to do to make this soup as sort of a linked workflow of what's going on. This also is a very good model to have for different problems, because as you see with this workflow, this isn't particularly efficient in the way it's done. If you were trying to make soup quicker, you could have multiple people do this workflow, but nothing about this workflow would let you split it up efficiently. And so if you are able to sort of change the way it's organized, here we have an example there, where it's exactly the same workflow, but you make it more aware of sort of its dependencies, you now have tasks that you can split up. So the person who's buying vegetables, the person who's buying meat, and the person who is heating the water doesn't need to be the same person, and you don't need to wait for the vegetables to be chopped to start heating the water. You can start heating the water immediately. And so this is the kind of approach you want to have, where if you can describe the task you're doing in this workflow manner, you're able to split it up much better. You're able to communicate it to someone else a little bit easier. And it gives you a very clear representation of what's going on. That if you have a giant pile of code like this, and you show this to your advisor, they probably won't really know what's going on. It's very difficult for someone else to inspect your code and figure out what's happening. Whereas if you have a workflow like that, it's fairly straightforward, and someone can ask you questions about why this step comes in this order, and it makes it a lot clearer for someone going through what you're doing. So the last thing we'll cover today will really be this idea of directed acyclical graphs. So unless you're a computer scientist or a mathematician, you probably haven't come across that term before, but it's really just a very complicated way of saying there's no loops and that you have a order in what you're doing. And basically this idea has come to kind of dominate the workflow or workflow world and the big data world at the same time. And so if you can express what you're trying to do as a directed acyclical graph instead of a list of specific operations, you have the ability to distribute, to be fault tolerant, to scale, to handle much larger, more complicated problems very easily. And so here are sort of a number of tools that you may or may not have heard of. Apache Spark is one of the major big data tools or platforms that's used for, analyzing customer records, going through logs, figuring out what ads are going to be clicked on. Spotify has a tool called Luigi, which they use for making predictions to kind of come up with better predictions for what you want to listen to. Airflow, I think, is from Airbnb, and they use this to try to set pricing and optimize which apartments you find at which time. KNIME is a tool we'll use in this class. TensorFlow is a tool many of you have probably heard of. It's from Google. It's for doing sort of deep learning, but it also has this basic directed acyclical graph approach. And then PyTorch or Torch is another deep learning tool that has this inside. And basically what this means is you are able to describe whatever you're doing as a graph. And so when you think about how programming or how you typically program things, you write a bunch of lines of code that are very, very imperative. So you're like, create an array, copy this data into this array, then go through each point in the array and perform this operation. And that's not a DAG. And so what a DAG is where you sort of create the graph that you're doing first, and then you run the computation. And the advantage of this approach is that you let other tools, which are much better suited for doing the computation, come up with an efficient way to run it. And so here we have an example of two images. So we have very small images, and we have their representation as a graph. And so you have one image there, which is created with zeros, and that's what it looks like. It's very simple. This is a Python tool called Dask, which lets you do distributed computations on really large arrays, but you don't need to worry about that. But now, let's say you want to add the images together. So you want to go image 1 plus image 2 is image 3. And here you can now see that you're able to create a graph. And so what you've done here is you actually haven't added any data together. You've created a representation of what this adding looks like when it happens. Now you can make it more complicated, so you can subtract 10 from one image, multiply another image by 50, and then you just make that graph bigger. And if you go beyond just sort of these simple little operations, you can take a big image. So here you have 1024 by 1024, and we describe it as being broken up into little chunks. And so we have little 512 by 512 chunks that we look at. That's the graph we get. And then if we want to add these two images together, we now see that rather than dealing with a whole image, you're dealing with a number of little chunks. And you can start to group these chunks together in order to come up with new chunks at your output that you're analyzing. And so you don't need to worry about understanding this code or how any of the chunking works, but just that you have this approach where you create graphs and workflows and you let other tools do that optimization for you. Because if you were to do this yourself, you would have to come up with some way of breaking up an image into little pieces and then figuring out which piece needs to be added to which other piece. And that's very complicated. And if you do it this way, it makes life much easier. You can now do more complicated steps. And so here, like matrix multiplication, if you have an image that's divided up into a lot of different pieces, matrix multiplication requires, comparing or taking parts of each piece, putting them together, and so you end up with these more complicated operations. If you now then multiply it by the original image, you end up with something back there. And now to take kind of the last thing of, if you wanted to then do a convolution on this, which is sort of one of the base operations for machine learning, you end up with this then much more complicated graph. And so that if you express things as a graph, you're able to make these and you're able to give them over to tools which are able to make them efficiently run. And when you specify everything directly, where you get immediate evaluation, you don't give other tools the opportunity to make things more efficient. And that's really the primary distinction we focus on here. And so we won't really talk about deep learning at all in this lecture, but just to appreciate why these graphs are so important, we'll look at one of sort of the state-of-the-art models. And so this model wasn't used for the captioning, but for similar kinds of tasks, where we have what's called ResNet 50. So this was developed by a group from Microsoft. And the model itself, so not the graph, just the model represented in graph form, looks like, there it is, looks like this. And so don't worry about all these operations, they're fairly straightforward. But to go from the input to the output looks like this. And so those are all of the steps that need to take place. And so all of those are image processing operations that you're using in order to classify with 1% accuracy if this picture is a picture of a dog or a cat or a cow or whatever. And so there's a huge amount of processing that needs to be done, and you need to make sure the steps are done in the right order with the right parameters, and this is a very reasonable way for keeping track of this. We then have the full graph, And so this is potentially something that you're better off exploring on your own. And so this is an interactive representation of that whole network or whole workflow where you can zoom in and then you can look at each operation and what's happening inside of each one of those things. And so none of the steps that are going on inside are very complicated at all. It's all addition, multiplication, subtraction, division, some average calculations, some very basic steps. But when you have lots and lots and lots of them together that are done in a very reproducible way, you're able to solve incredibly complicated problems. But the value comes not because you have some magic operator here that's much smarter than everything else. It comes from the fact that you're able to lay out and reproducibly execute all of these things and that you're able to do that quickly. And so if you look at that very complicated graph that we showed before, if you were to try to implement that yourself and execute it, it might take 60 seconds to run on one image. And when you make that graph and you have it executed on a modern GPU, you can now execute 30 images a second through that same graph because you're able to benefit from efficient operations that NVIDIA and other companies have spent a lot of time developing. And so it's really about how can you be as lazy as possible and let other people who really focused on implementing these things well do as much work as possible for you, is ultimately what all of this comes down to. And so trying not to reinvent every single operation that's been done and do things efficiently. And so basically, if you're going through an image and you have a for loop and you're going point by point by point, there's a pretty good chance you're not doing it very well and someone else has already solved that problem, because people have solved not every problem you come across, but almost every one in very efficient ways. So that's it for the lecture, unless there's any questions. Yeah.
So, anything, especially the last part, makes you wonder a bit what would be in your opinion, the role of computer vision in the sense, as you explained it before, one of these ways of analyzing the problem by caring actually of how the image, what kind of properties does the image have, what features could I look for?
Yeah.
So will the last part relatively take over the role which computer vision had?
I think it's pretty difficult to answer that in sort of general, because it's almost kind of a religious question of sort of what do you believe in most. I think it's quite clear that there's a huge number of problems that computer vision could never solve, that deep learning has been able to solve much better. But these algorithms are still being designed and tested and built by people. And while it's a bit difficult to appreciate how a person contributed much to these giant structures, because they look like just huge, massive things, this insight here, for example, this add operation, that you do a bunch of processing on this side, and you do a very little processing on this side, and then you add them together, was a human insight, not a computer insight. And so there, it's a bit difficult to get into sort of why residuals are a good idea, but the idea that you can bring some of the knowledge you have and some of the understanding of the system in order to improve how a computer model is working, I think is where, at least for today, the development is. Of course, there's papers from Google and DeepMind that show that they have computers that can build machine learning algorithms better than people build machine learning algorithms. But there's still some value in understanding what problems are trying to be solved and in looking at what these algorithms are actually doing. And so, it's very easy to build an algorithm that gets a very high performance, but if your algorithm can't explain itself or was focusing on completely the wrong information, then it's not going to be a very useful algorithm for people to use. And so I think that's where a lot of it will come in, where the computer vision will be much more of, where does the algorithm fail? And how can we avoid those situations? Or what happens if someone puts something absolutely ridiculous inside it? Like they have those images, they have stickers right now that you can put on stop signs that have very, very weird patterns on them that make a deep learning algorithm think the stop sign is 120 kilometers an hour. And so if you put this sticker on there, it wouldn't confuse any person ever. They might think there's a weird sticker on there. But the way the algorithms work, they're very sensitive to these tiny patterns. And you would now have a car getting into an accident. Now, hopefully people don't do that, but it's the kind of situation that comes up quite frequently. And I think we have some examples open. Yeah, here. So that here is, again, this sort of ResNet algorithm. And we have an image of a panda here. And we can add tiny little noise patterns to it. And the algorithm goes from being 90% sure it's a panda to being 100% confident that it's a porcupine. And this wouldn't confuse any person. No one would look at those patterns and say that they mean anything at all. But for an algorithm that performs 11.4 billion operations in order to make this decision, it's completely confused. And so I think there's still clearly lots of room for improvement, because what these algorithms are doing right now is very far from what we're actually doing. And I think they're a lot better than what computer vision was doing before these techniques came along, but they're by no means the final solution for everything, for every problem that comes up. There's a lot that can't be solved by just optimizing accuracy. But yeah, it's definitely an open-ended sort of question.